Добрый день, уважаемые коллеги. Начинаем очередное заседание Общеинститутского семинара Математического института Стеклова по математике и ее приложениям. Сегодня у нас докладчик профессор Драгович из Белградского университета и Сербской академии наук. Тема доклада – космологические решения нелокальной гравитации. Пожалуйста, профессор.
Добрый день, уважаемые коллеги. Прежде всего, хотел бы поблагодарить организатору Общеинститутского семинара Математического института имени Стеклова за приглашение сделать этот доклад. Я очень рад такой возможности, тем более, что меня с этим институтом связывает многолетнее сотрудничество. Я много раз был и провел немало времени в отделе математической физики и в отделе теоретической физики. У меня было и до сих пор есть плодотворное научное сотрудничество с многими учеными Математического института, особенно с профессорами Игорем Воловичем, Ириной Арефьевой и Сергеем Козыревым. У меня очень приятные воспоминания о моем пребывании в этом институте. Мой доклад подготовлен на английском языке, и поэтому мне кажется проще сделать его тоже на английском. As one can see from the title of my talk, I will speak about non-local gravity theory. Sorry for the telephone call.
Made the presentation full screen. Zoom it in.
It's Control L. That's it. I will speak about non-local gravity theory and its cosmological solutions. This talk is based on joint work with Ivan Dmitrievich, Alexey Koshelyev, Zoran Rakic, and Yelena Stankovic. We have used mathematical methods, first of all, pseudo-Riemannian geometry to construct valued non-local gravity model and obtain new, exact, and physically interesting cosmological solutions. Here is a plan of my talk. In introduction, I will say about some properties of the general relativity, which are related to this talk. Then I will speak about modification of general relativity, and in particular to non-local modification of general relativity. In fact, I will use this action here as a more general model for particular models. What we have here, we have integration over pseudo-Riemannian manifold. R is Ricci scalar. Lambda is cosmological constant. P of R and Q of R are some differentiable functions of R. And in particular, we'll have these three cases here, where when this P is equal Q as a functions, and in one case it will be equal to square root of R minus 2 lambda. In the other case, it will be equal to R minus 4 lambda. and in the third case, it will be equal to R. Here, f of box is an analytic function with respect to this box, where box is the Lambertian. After that, I will speak about cosmological solutions. In fact, I will speak mainly about this model with square root of R minus 2 lambda, and the corresponding two solutions. The most important for us are these two solutions. As we will see, this solution here is related to the dark matter and to the dark energy, and this one is a non-singular bound solution. And of course, at the end, I will speak about some concluding remarks. So, in introduction, first of all, several words about general relativity. General relativity is, in fact, Einstein's geometric theory of gravitation, which was formulated in 1915, and it serves still as a classical theory of space-time with matter. It is usually presented in this form here, where at the left hand side we have a geometrical sector, and at the right hand side we have distribution of the matter. It is really one of the most profound, the most beautiful physical theories, and it had many significant predictions of some physical phenomena, and they are also confirmed. For example, just to mention some of them, it's deflection of light by the sun, gravitational redshift of light, gravitational waves, gravitational lensing, black holes, and some others. One can say that it perfectly well describes the dynamics of the solar system. Especially, it was a big success when it is well described the perihelion precision of Mercury orbit. In general, relativity is still a starting point in our approach to any gravitational phenomena. And modern cosmology is based on general relativity, and this started just 2 years after it was founded. It means in 1917. Yes, it is a very nice theory, a very profound theory, but nevertheless, there are some problems. There are some problematic aspects. So one cannot say that it is a complete and final theory of gravitation. For example, as a problems, there is a problem when we want to quantize general relativity. Also, when general relativity applies to the universe as a whole, or at the level of the galaxies, it allows existence of dark energy and dark matter. But these are still hypothetical, and there are no laboratory evidence of these dark matter and the dark energy. Also, general relativity has not been tested and confirmed at very large cosmic scales. So we should be very careful when we apply it and obtain some results related to the very large cosmic scales and to the universe as a whole. Also, under rather general conditions of the matter, cosmological solutions contain Big Bang singularity, what is also one of the problems. I would like also to say that it seems unnatural that some theory, even when it is a general relativity, is valid and can be applied for all scales. For example, from Planck scale to the universe as a whole. As we know, physical theories mainly depend on scales and complexity of the systems, or also from some parameters. So any physical theory has some domain of its applications. Because of these and some other problematic aspects of the general relativity, there are many attempts to modify general relativity. What I will present here is a non-local approach to modification of general relativity, mainly non-local approach. Now I would like to say a few words what is so-called standard cosmological model. Like in physics of elementary particles, we have standard model. Here there is also what is called standard cosmological model. It is based on Einstein equation, which has, as I said, this left-hand side and the right-hand side. Left-hand side contains quantities from the pseudo-Riemannian geometry, and on the right-hand side is distribution of the matter in the form of the energy momentum tensor. At very large cosmic scales, and for the universe as a whole, we usually use Friedman-Robertson-Walker metric, which line element is given is this form here. What we have here, it's this A of t. It's a scale factor, cosmic scale factor, and it depends on the time, and it tells us how universe expands a long time. When we put metric elements of the metric tensor to the left-hand side, and to the right-hand side, this energy momentum tensor, where this rho is energy density and P is pressure, then we get what is known as Friedman equations, which are very, very well known. And what we have here, we have A dot, it's first derivative with respect to the time, cosmic time, plus K over A square. K is parameter constant, which can be plus minus 1 or 0. It depends on the universe. Is it flat, closed, or open? And here, this rho is, as I said, is energy density. The second equation is in this form here, where we have two dots, second derivative, which means in some sense acceleration, and have here rho plus 3p. In 1998, it was discovered the accelerated expansion of the universe, what was unexpected. And the accelerated expansion of the universe, it means that this A double dot over A, which is in a sense acceleration of the universe, is positive. Yeah. So the right-hand side has also to be positive. It means that rho plus 3p has to be negative. In other words, because rho is positive, then P pressure has to be negative. It means that we have some new kind of the energy of the matter where pressure is negative. It gives some kind of the repulsion of the universe, and because of that there is this accelerating expansion of the universe. Also, standard cosmological model contains what is called dark matter, and it is related to big velocities in the, first of all, spiral galaxies, but also in general in the galaxies. And now I would like to say a few words how it is introduced, this dark matter. Here we have a spiral galaxy, and in the center of the spiral galaxy, that we have a coordinate system with these two axes. On this axis here is radial distance of some stars. It is distance from the center of the galaxy to the star. Yeah? And on this axis, we have velocity. Velocity is radial velocity of a star, because in galaxies, spiral galaxies, we have a rotation, and there is this radial velocity. So these points here are experimental results, observational results. Astronomers can measure distance from the center of these stars, and also can measure velocity of the stars. And these points here correspond to what they found. We see here that with the distance, velocities have some even increase with the distance. But since here can be applied Newton gravity, and Newton gravity is an approximation of the general relativity. According to the Newton gravity, these velocities of the stars should be at this line here. In fact, astronomers can also estimate how much there is visible matter here. And with respect to this visible matter, one can calculate, one can compute where these velocities of the stars should be with respect to the distance. So they should be, according to the Newton law, or in other words, also to the general relativity, at this line here. but in fact they are at this line. So there is discrepancy here, and there are two approaches how to try to describe. One approach is to say that there is some additional matter here, which is attractive and which keeps these these stars at these distances with these velocities. And such additional matter is called dark matter. And such additional matter should be about 5 to 6 times more than visible matter. The other approach is to try to modify law of the gravitation, to try to find the modification of the Einstein theory of gravity, and to find some force which will keep these stars at these distances with these velocities with only this visible matter. So there are these two approaches. But this hypothetical additional matter is not yet confirmed, and it's not experimentally detected in laboratory conditions. So Einstein equation of motion, also with the lambda term and with the hypothetical dark matter, represents what is called the standard cosmological model. So we can conclude, according to standard cosmological model, that there is, in such case, if it is true, then it should be about 68% of dark energy in the universe, and some about 67% of dark matter, and only about 5% of the ordinary matter, or visible matter. So about 95% of the matter, of the energy matter budget in the universe, according to this model, should be some dark side of the universe. Because of the reasons which, as I said already, that dark matter, dark energy are not experimentally detected, and that the Einstein equations of motion are not verified at the very, very large cosmic scale. So there is a reason, there is a sense to try to modify general relativity. And here is Einstein equation of motion, as I already said it before. And as we know, it can be obtained from the Einstein-Hilbert action by variation of this action with respect to G mu nu, which is a metric tensor. And we have here only R, scalar curvature. And when we want to modify general relativity, we don't start from this equation here, but we start from the Einstein-Hilbert action, and modify, do modification. It means to replace this R here with some function which in general can be function not only of the R, scalar curvature, and the lambda, and the Ricci tensor, and the Riemannian tensor, and the D'Alembertian, and also some other quantities from the pseudo-Riemannian geometry. And there are many modifications, especially after 1998, when it was discovered, as I said, accelerated expansion of the universe. Yeah, unfortunately, there is no some theoretical principles or principle that could tell us in what direction to look for a modification. So there are many approaches, there are many models, and I will just mention a few of them. And the most known is f of r. It means that here at this place, instead of the r, we now take f of r, some function of scalar curvature. It can be an analytic function or a polynomial or for example, rational function. And people do it in many cases and find some also good solutions, for example, for dark matter or dark energy. But many of these models have problems at the other scales. So there is not so far generally expected modification. There are also other modifications, but I will only to focus on no-local modified gravity. What it means that we use also D'Alembertian here. It can be some function of the some combination of D'Alembertian and the R. Also some other constructions in general, maybe pseudo Riemannian geometry. And there are mainly two approaches with no local modification. One is when people use inverse of the D'Alembertian. For example, in this form here, where there is some function between this R and R. There is some function of the inverse D'Alembertian which acts on the scalar curvature. And for example, it can be also in this form here. But I will focus in my talk, I will focus on the analytic no-local operator, which is given in this form here as an analytic function of the D'Alembertian. Now the question is, what is the motivation to use this analytic approach? For example, addition of D'Alembert operator in Einstein-Hilbert action improves renormalizability. Also, we know that in p-adic string theory, there is an exact Lagrangian, which at the 3 level describes scattering amplitudes. And we see here that we have this kinetic term with this exponential function of the D'Alembertian. And also in string field theory, there are also some Lagrangians, approximative Lagrangians, which contain D'Alembertian in the analytical, mainly in the exponential form. And these kinds of non-locality are used in matter sector of cosmological models by Professor Sarefio and Volovic with their collaborators. So these are, in some sense, motivations why we use operator, this non-local operator, in an analytic form. Our main non-local model is presented here, where we have, which can be written in this form here, where we have square root of r minus 2 lambda. Here, this operator with the Lambertian, and also square root of r minus 2 lambda. You see, if we take that this operator here, f of box is equal 1 plus this italic form f, then we'll have a usual term, r minus 2 lambda, is in the Einstein theory, and additional term in this form here. How we can get this? We can get this in the following form. If we start from r minus 2 lambda, what we have usually in the Einstein theory with the lambda term, then we can write it in the form of product of square root r minus 2 lambda, square root r minus 2 lambda. And then we can put between this product, inside this product here, we can put this operator here, and then get this term, which is just in the Einstein case, and this this one, which is our term. This is our model. It is not considered with our other researchers. Why this is important? This model is for us the most important because it gives very important and exact cosmological solutions. First of all, these two solutions, where this one contains effects which are usually attributed to the dark matter and to the dark energy. And this one is non-singular. So these two solutions are exact, and they are solutions of, for this model here. They are cosmological solutions for this model here.
Excuse me, can I ask you?
Yes.
What is your choice for the function f of the Lambertian?
Function f is an analytic function, and in the process of the considering this model, we find an explicit form for this function f, and it will be presented in the sequel of my talk.
Okay, thank you.
So because we need to derive equations of motion for such model, we start from some more general model where we have these functions P of R and Q of R, which are differentiable functions. And the F of box is in this form here. And for simplicity, just to see better effects of modification, we don't, and it is not necessary at this stage, to use ordinary matter. So we derive the equations of motion, and they are in this form here. It looks rather complicated, rather complex at this at the first sight. This part here corresponds to the usual Einstein theory of gravity, where G mu nu is Einstein tensor, and lambda G mu is a cosmological term. Here is additional part of the equations of motion, which is a result of the modification, where this K mu nu is given in this form here, and this this F is this function here, where this prime means derivative with respect to the R, to the scalar curvature. Yeah, in the four-dimensional case, there are in general there are 10 equations of motion from here. But when we apply it to the cosmology, since we take for the universe that it is homogeneous and isotropic, it means with Friedman, Lemaitre, Robertson, Walker metric, then because of the symmetry, in fact, we have only two linearly independent equations of motion. It is reduced to these two linearly independent equations of motion. And they are usually trace when we take trace from the previous equation, and 0, component. So now we have two equations of motion, which we can then apply for the description of the universe, to try to find cosmological solution. This is also rather complicated, but fortunately, when we take that P is equal Q in these equations here, and when we use this equality here, which is in some sense eigenvalue problem, it means that when we have this D'Alembert, which acts at the function P of R, we get again P of R with some here parameter P, which we try to find. So what is very important for possibility to solve this equation is to get appropriate such equality. And fortunately, we succeed in it. So we have this action here, and we have three models. The first one is this one, where we take P of R is equal to Q of R is equal square root of R minus 2 lambda. So I will mainly speak about this model here because it is for us the most important. So what we do, we form this equation here, where this box contains h of t. H of t is a Hubble parameter, Hubble function, which is related to the solution for the equations for the scale factor in this form here, where we have first derivative of a over a, and r of t in the case of the Friedman Robertson-Walker metric, it has this this form here, this double dot. So in other words, second derivative with time of this a, and so we can suppose some solution to find this parameter here, this function, and also this one, and put this one here and this one here, and try to find such solution. Yeah, this is the idea how we do it. Now, now I consider this the most important model for us, where we have the square root of r minus 2 lambda. And this f of box is equal to, to the analytic function of box. So we start, yeah, I want to show that, and it was shown by us, that this cosmological solution satisfies, satisfies this equation here. So for this solution, for the scale factor, we can calculate, we can compute this R scale scalar curvature to put it here, and also we can calculate this D'Alembertian, where Hubble parameter is given here, and then we shown that there is such equality, and and that equations of motion are solved if we take only the following two conditions for this function here. And finally, then we can find an explicit form for this f of box, which is in this form here, box over lambda, exponential function of the box over lambda. What is very important here that that in fact this solution here mimics dark matter and dark energy. Why? Because this factor here, t, time t, cosmic time t, to the power 2 over 3, is just what we have in the standard model with the Einstein theory of gravity, with the general relativity, where for the universe we have matter dominance. Then scale factor has this this behavior. So also we see it in the Hubble parameter that we just have this part here, which corresponds to the matter, to the Hubble parameter for the matter dominance in the ordinary case, in the standard case, with the Einstein theory with matter dominance. And here we have also what is related to the dark energy. One can calculate. One can first construct analogs of the energy density and the pressure, and to see what is it for this model. We computed it, and it has this form here, t to the power -2 lambda term times t square, and only lambda term. Also similar is for the pressure. What is very important that when we take this ratio of this, which is related to the parameter for the equation of state, then when we take the t cosmic time tends to infinity, we get -1, which also corresponds to the dark energy. Here I presented some parameters from the Planck experiment with Planck satellite for the Hubble parameter, for the matter density parameter, lambda density parameter, for the age of the universe, which is 13.8 billion of years, and also this W00, yeah, for the for this parameter of the ratio of pressure to the energy density. What's important here that this Hubble parameter has 67.4 kilometers per second per megaparsec, and we want for our model to calculate some of these parameters and to compare with these parameters for the Planck mission 2018 results. So when we take for the Hubble parameter expression, which I presented already, and for our cosmic time, we can take the previous values for T0 for the age of the universe, and for the Hubble parameter. Then we can calculate, we can compute this lambda. When we do that, we get for lambda that it is 1.05 times 10 to -35 seconds minus square in units when we take that the speed of light is equal to 1. If one calculates this lambda in the standard case, in other words, this lambda in the standard model is this value here, 0.98, the same, almost the same, very similar to our value here, in good agreement. One can also calculate, and we do that, one can calculate the minimum of the Hubble parameter, the time, the cosmic time when this Hubble parameter will have minimum, and we computed it, and it will be in the future when the cosmic time, according to our model, will be when it is 21.1 billion years. And in that time, this cosmological, this Hubble parameter should be 61. It means less than it is usual. Yeah. And also one can calculate calculate the beginning of the expansion of the or the acceleration, and we obtained that it is close to the 6 billion years ago. One can calculate also other some parameters, and we get very good agreement with the standard model. Also, we have some explanation for the coincidence, so-called the coincidence problem, that what is related to the dark matter and then dark energy are of the same order of the magnitude. One can calculate this bound, this bounce, a non-singular bounce solution. It's in the similar procedure in the previous case. I have no time to speak in detail about it. So it's also in good fashion. There are also solutions when we take that the universe is closed or open. Then we have also these cosmological solutions which are exact, and which is also very interesting. All these three solutions which I presented are related to this model, which we call non-local square root gravity model. Now, just a few words about these other cases. When we take this model here with R minus 4 lambda, then we have cosmological solution, also exact cosmological solution with the similar procedure. And this solution is important because this is some mixture of the solution with radiation dominance and energy dominance, and this energy, this lambda part. So this solution is relevant for the beginning of the universe, sometime from after the beginning of the Big Bang. Also, there is a non-bounce, this non-singular bounce solution, and for the case RR, it is considered with linear ansatz, and it was obtained this cosine hyperbolic solution by Biswas, Kuivis, Thomas, and Dursigel, and by Kosheyev and Vernov in this form here. And my group, we obtained solutions and considered solutions in this form here. Now I'm going to the concluding remarks. What I want to point out, it's that that we have this model here, which is the most important for us, where this f of box is also given in an explicit form, and that for this model, where we have a flat universe and lambda different from 0, we have this solution which imitates dark matter by this factor here, and dark energy by this one here. I also presented that computed cosmological parameters for this model here are in good agreement with observations. Now the question is, what can be the next step? The next step for this model here is to check validity of this model at other space-time scales. First of all, at the galactic scale, also for the solar system, also to see is there some inflation for this model, and our preliminary results give us a positive answer to this question. So we want to proceed with this model here. In all the previous three cases, models, not only this one and also the other two models, we have a solution of this form here, which is a non-singular solution, cosmological solution, what is also very important. Yeah. Here are some relevant references. What is the most important of these references for my talk are these first few references. And at the end, thank you very much for your attention, and best regards from Belgrade.
Thank you very much, Branko, for the very interesting and very nice talk. Questions, please. I have a remark and some comments. First, you consider rather general action, this function f of delta, f of box.
Yes.
Some years ago, this Professor Valery Kozlov, we published a paper. They consider the eigenvalue problem for hyperbolic case. Actually, you have hyperbolic equation and eigenvalue problem. Your very nice equation, the Lambertian action to r minus 2 lambda equal p and so on. So maybe it was to consider some additional conditions to restrict the function f of delta by using, for instance, what we did with Kozlov. We could discuss this later, because in elliptic case, people obtain eigenvalue problem only because consider L2 space for eigenvalue problem, integrability condition. You have very similar situation, and maybe additional restriction could be helpful. And second remark is this. Let us recall the brief history of the universe. First, inflation, exponential expansion, then uniform expansion, and once again, after 10 billions of years, which we have even now, again, accelerated expansion. So what do you think if consider the following function f of box in your theory? First, exponential function times some function polynomial of squares, some simple behavior of time. Then another exponent, but with smaller cosmological constant. So not just one exponent function, but two, sum of two, plus maybe the third term describing the universe in uniform expansion. Then you will get the description of the whole history of universe, not only dark energy modern time. What do you think?
Yeah, first of all, thank you for your comments about your work with Professor Kozlov. I will take it into account in our future investigation. It's very good comment, and I think it will be also useful and important for our investigation. What's the matter of the description for in this model of the universe for the whole evolution, not only what was already was, but what will be in the future. We think to combine these solutions to take these solutions, some of them for the beginning, some of them for the later time, and some for the future. And I prefer the universe which is closed and which would be oscillating some cyclic universe. We have for our main model, we have the solutions for the closed universe. So we will combine these solutions. Also, we will find some other solutions which which will not be exact, but which will be approximative. And then we hope that we'll be able to present a complete, more complete picture of the evolution of the universe.
Thank you very much. Let me say again, stress again, that I like very much your eigenvalue looking equation, the Lambert connecting to square root and so on. Very nice equation. More questions, please?
I have a question. Thank you for the very interesting talk. Do I correctly understand that the problem in the standard cosmology is dark matter? The dark energy problem can be avoided by the inclusion of the cosmological constant, but dark matter is a problem which forces us to modify theory.
Yes, you see the problem in the standard cosmological model. The problem with dark matter, first of all, with dark matter is that it is investigated already for the many years, and people got many grants for investigation. It as a particles, the corresponding particles, but also to confirm it in some sense at galactic scales. But unfortunately, no good results. It is not confirmed in the galactic scale. And also there is no experimental evidence. Even supposing all known particles and even some particles in some new models, supersymmetric and so on. So in this model here, we took from the beginning lambda term, and it is also in the standard cosmological model, also lambda term. So it's the same. But what is unexpected for us, and what is very important, that we get here effects at the cosmic scale, effects which are usually attributed to the dark matter in the standard model. So, so far in this our model, we don't need existence of the dark matter. At the cosmological scale, we can describe effects which are like dark matter. We can describe it by our model. We don't need dark matter. So the problem is in the contemporary cosmology, the problem also in the physics of elementary particles is the problem with the existence of the dark matter. I think that it is not so big problem with the cosmological. When we take that the dark energy is just cosmological constant.
Okay, thank you.
More questions, please.
Maybe a short question, if possible.
Yeah, please.
Привет всем. Бранко, спасибо большое. Because we already discussed several times on this point, can you say something a little bit about some progress concerning the concrete theoretical or effective potential related to your research? Because different potentials can give some different results, at least in some particular cases. So can you say something a bit more about that?
Yes, we considered it, but we did not publish it yet. So I didn't talk about it. Preliminary results we have about it. But what is interesting maybe to mention now is that in some sense from this model here, which is the most important for us, one can get this model R minus 4 lambda in some approximation. In fact, when we take that lambda is bigger than R, we can approximate the square root of R minus 2 lambda, and then we can obtain something like this model here. So there is some connection between these models. So the basic model is this one. Yeah.
Okay.
Okay, Branko, thank you.
Branko, please show again your eigenvalue equation. The Lambertian acting to R equal to.
Okay, yes, I will show it. For example, for this, our most important case, yeah. Okay, for example, for this one, yeah. You see, we wanted to show that this eigenvalue problem is satisfied for this solution here. It means as eigenvalue problem, it means that we have eigenvalue, this -3/7 lambda, and the eigenfunction is then r, the square root of r minus 2 lambda, where this r contains this solution here, because you see r is expressed in terms of the cosmological solution in this form here. So one can calculate this r of t, and then check this equation, yeah, and we succeeded. And in fact, one can say in all our case where we solved the equations of motion, we succeed to solve it owing to this eigenvalue problem. That we succeeded to solve this eigenvalue problem, and we get exact solutions, which are special solutions for the equations of motions.
R of t equal to 6 and so on, yes, in this case.
Sorry?
Eigenfunction, R of t equal to 6 and I dot and so on. Is it true?
Eigenfunction for this problem, eigenvalue problem, is square root of r minus 2 lambda.
Yes, but what is r?
R is scalar curvature.
Yes, it is equal to this.
Which contains this cosmological
very beautiful
cosmological solution, and also in this box, in this the Lambertian, we have also this h of t, which is Hubble parameter, and it's also related to the cosmological solution. So it was very important to combine this all together and to find this solution.
A of t is an arbitrary function.
R of t?
Yeah, no, A of t.
A?
Yeah.
Which A?
Hubble constant equal A dot divided to A.
This one?
Yeah, the function A of t is an arbitrary smooth function.
A of t. A of t.
Yeah.
A of t, for the beginning it can be arbitrary function. We can look in such a way.
Okay.
Yeah, we can say that we don't know this A of t, the scale factor, and then to try to solve this equation here. Yeah. But one can in the opposite way also to do that. Okay.
Yes, thank you very much. Fantastic formula. So, are there more questions?
Let me ask one more question. Just yesterday, I saw a news on some popular science site about a paper in this summer paper. Some authors, the authors are Pardo and Spergel, that about alternative gravitation theories, and they claim that alternative gravitational theory, cosmological theory, which aims to avoid dark matter, the existing theories fail to reproduce a correct cosmic microwave background polarization spectrum. And if such theory exists, it should have it should be very peculiar. So they cast some doubts on the existence of such theory because of certain cosmological observations, like a polarization spectrum. Could you could you comment? Do you know this work, and or could you comment on this something?
Yeah, we didn't consider it yet, so I cannot comment. Of course, any model has to pass many tests, and so far there is no model who passed all tests. Yeah, so we'll see how much we will proceed with this model, but so far it's very good.
Yes, I agree. So it recalls me that Copernic also was strictly speaking wrong, because he thought about circular orbits, not elliptical orbits, but the idea was correct. So yes, I agree with you that these results are very interesting.
Okay, let us finish this very nice talk. Thank you very much to Branko and all the participants. Thank you very much. Bye-bye.
Bye. Thank you very much.
Thank you.